welcome back, guys. So in this video, we're going to be covering how to solve the Laplace equation in 2D. So in another video, we already solved the heat equation, the PDE, for a one-dimensional. So if you do the heat equation for two-dimensional, and then you do steady state, you will get the Laplace equation, or the steady state Laplace equation, which you can see over here in the picture in green, all right, in the screen. Basically the thing is steady state. That means that all the side that deals with time just went to 0, and we are left only with the x and y coordinates, right? X and y terms. So we're differentiating this function u as a function of x and y. In another video, once again, we already solved how to find basically derive the steady state Laplace equation. So I'm not gonna go into detail on that one. So for this one, all we're gonna do is just solve this one. So I'm already giving the solution right here. All right. All we need to do is find the an constant, and we will use that to plug it into our equation so we can do our plot. So for this one, we have a square. You can see it has the square looks like that. It's in blue, and we want to find the potential. So let's say this is like an area that we have voltage. So we want to find like the voltage, whatever the voltage is. And we have the following conditions. So on the upper side, we have it that it is equal, or the u in this case will be the voltage. It's equal to some function f of x. And this is for all time, right? This is a very steady state. Then for every other side of the square, it's grounded. So there's no voltage, right? The sides are equal to 0. The length for this square, it's 2 centimeters by 2 centimeters, right? Length and width. A, it's 2, B is 2. And we have the function here, which is sine of pi over 2 times x. And that is our, basically our givens or variables. So you can see our equation here for u of xt, it's equals to the sum from n equals 1 to infinity of an star times sine of n pi over x over a times hyperbolic sine of n pi y over a. Once again, we already derived. If you want to see how we did that, there should be a video in the description somewhere over here on top, so you guys can look for that one. All right. Anyways, so let's find an star. So we got to do that for every one of the n's. So let's start that one. Let's start doing that for n equals 1. So at n equals 1, we'll get that a1 star is equals to 2 over a, which is 2, times hyperbolic sine of n, which is 1, so just pi, times b, which is 2 over a, which is 2. And this is the integral from 0 to 2, which is a, right? F of x is sine of pi over 2x times sine n is 1, so pi over 2 times x dx. So once again, we're going to have a sine times sine. At least for this case, you can see we don't have to use the identity we used in the other video, which if you want to see, there should be already a link also over here for the heat equation PDE, where we use the identity of a sine times a sine to write it into cosines and just solve it much easier. But at least for this case, because they're the same sign and they have the same information inside the parentheses, we can just convert that into a sine square. Okay, so if you can see, we simplify some things. The 2 over 2 cancel, so we end up with 1 over hyperbolic sine of pi. In this case, sine hyperbolic of pi is not 0, because the hyperbolic is just like a combination of exponentials. So it's not 0 for sine hyperbolics. And we're still integrating from 0 to 2. And we're going to integrate sine square of pi over 2x dx. So this will be 1 over hyperbolic sine of pi times something from 0 to 2. So we're going to be integrating this, and let's see what we can. Let me just move things around here a little more. So if you have a table of integrals, right, we can rewrite sine square as 1 minus cosine square and so on. But if you have a table of integrals, which we do have one in the book, right, that we're using in class, that we use for analysis 2. If not, you can just Google it. What is the integral for sine square? And we will have that the integral should be the following, which is 1 over 2x minus sine of what we have, which is pi over 2 times x. Wait, no, it's twice that. So it's twice of that, which is just pi times x. And this is divided by, so inside is pi x times 2, which would be 2 pi. All right, once again, you can just find the equation solution. I think to write like a general approach, it will be like sine of 2a over a times 2. It's something like that, right? But this is the actual answer. All right, if you Google it, this is what you are going to get. All right, so let's integrate this. So let me just, then this is equal, not integrate, right? I mean, evaluate. So this is 1 over hyperbolic sine of pi. And this is times 1/2 x. So this will be 2 over 2 minus sine of 2 pi over 2 pi. And this will be minus 0 minus sine of 0 over 2 pi. And of course, well, this one's cancel 0, sine of 2 pi is 0, and 2 over 2 is just 1. So we are left with that an, or not an, a1 star is equals to 1 over hyperbolic sine of pi. This is what we get for our solution. Of course, we can continue adding more terms. If we do, you might find out the next ones could be 0. I mean, you can try that yourself. See if a2 is 0 or what value we get. Once again, these ones are just approximations, so we don't have to go into depth. But if you were to see that if you put n is 2, we get in the bottom, once again, 1 over hyperbolic sine of 2 pi times the integral of sine of pi over 2 times sine of 2 pi. I have to do the difference in cosines. And we integrate them, we're going to see we're going to get sines. Once you evaluate any one of those sines, it's going to be 0. And for the other one that we're going to get sine of pi over 2, or if you're going to plug that in, once again, for whatever value of x, when x is 2, which you're going to get sine of pi, so that's your 0, and so on. So it seems that we might be ended up getting just 0 sort of few of them. So you can try that, check if it works, but at least for this one, it's enough for our code. So now that we have this, we can rewrite our equation. So I will write it as that u as a function of x and y, it's equals then to sine of, well, n is 1, so sine of pi x over 2 times hyperbolic sine of pi y over 2 divided by hyperbolic sine of pi. And this is what you will put in MATLAB. This is what you guys will put in MATLAB, in this equation right here. So once again, do different values for x. So for x, do from 0 to 2. Do a matrix from 0 to 2. And whatever increments you want. Same thing for y, 0 to 2. All right, that's our square. I'll plug this in. You already have the code, right, to do like a surf or something like a 3D plot. And that's pretty much. I mean, we already did this. All I have to do once again is just write that in MATLAB. Once again, just make sure that every multiplication you put the dot so that you do get the correct matrices. So that might be one of the errors that you might be getting, but at least that part you can figure out on your own. So let's go to MATLAB and let's see what we get. So you can see from here, these are the 4 plots that I get. So what I'm asking for, it's find the equation u, which we just find out. And then everything else is just plots. So a plot, 3D plot of Laplace. So you just x, y, and then z, which is your u. Just a surf plot. The next one is a plot of electric potential versus length on the x side, electric potential versus width on the y, and then a contour plot, so as if we're seeing it from the top. Once again, and all of these commands, I think they're already given to you. All you have to do is just plug in the correct values. And this will be the four graphs that you get, right? So we have this one, which once again, if it wasn't MATLAB, the actual MATLAB, not on the computer, I will be able to show you. So if you see from the side, it looks like a sine curve, right? That's the sine we get based on the x. And we see from the y, we get the hyperbolic sine, which is an exponential, which seems decaying. And then you see from the top, you can see the yellow part is like the voltage. We get up to 1 volt, and everything else is decaying. So it's something like if you had like I don't know, like a wire that fell into the floor, and the closer you get to the wire, the more electricity there is. You could do the same thing here. Instead of being voltages, it could be heat. So the closer you are to the surface, to the heat source, it's gonna get hotter, but the farther away is gonna decay and be cooler. So this is once again how it looks like from the front at a constant y. So at y equals 2, and this is how it varies by x. You can see it's a sinusoidal, it's just like one wave. This is how it looks like for looking at a constant x. So it's an exponential curve, right? It's a sine hyperbolic, it's an exponential curve. And then the next one that we have over here, it's as we're looking here from the top. So it's a contour plot, and all of this code is given to you. And this is just where you guys can practice how to do this kind of equations, this kind of graphs, and you guys can do them for your senior design, for other labs, other classes. So it looks cool. And once again, this is how it looks from the top, from the width and the length, looking at the top. And you can see as we move away, the potential in volts decreases. So that's it. This is it for the MATLAB projects for the heat transfer. If you're watching this video because you wanted to learn also more on the Laplace equation in an application from analysis 2, you're welcome. So this is some of the things you might do. So if you're watching this video from analysis 2, just remember you might end up doing this also for heat transfer in a couple semesters. So don't forget about that. So keep that in mind that you will have to do this again. All right, so that's it. I will see you guys in the next video. Until then, good luck.